welcome to the report of the Specialist Committee on Maneuvering in Waves. My name is Gerhard Strasser and I'm from Vienna Model Basin. May I introduce the chairman of this committee, specialist committee, that is Professor Hironori Yasukawa from Hiroshima University. Professor Yasukawa, the floor is yours. Please start.
Okay, thank you very much. My name is Yasukawa from Hiroshima University. This time, I'd like to introduce the achievement, the activity of the Specialist Committee on Maneuvering the Waves. So then you can see this slide. Chairman, this is my name. These are other members here. So then this by cooperative study with these members, so we made the report. Okay, this is a task. So then this, as you can see, this time I'd like to talk about some keyword. The second is you can find the keyword, the state of the art. The third is a guideline. So then is the 5, so find the minimum power requirement. So then the 6 is also we find the minimum power requirement. 7 and 8, these tasks also related to minimum power requirement. So then this time I'd like to talk about the achievement about the task of the minimum power requirement and some the state of the art. Originally, we planned to add the result of the Simon workshop, but we did not mention it because it was postponed due to the influence of the coronavirus. So this time, my main topics are here: state of the art, minimum engine power, and conclusion and recommendation. Okay, the first one is the state of the art. In the report, so that we can find out the 5 subsections. First one is the experimental method, second, numerical method, third, the steady sailing performance and maneuvering limit wind and waves, fourth, wave effect on ship maneuvering in shallow water, and the fifth, additional aspect of maneuvering simulation in waves. So here, I would like to introduce first one, the experimental method and numerical method. So in an experimental method, so there are 2 types of the method. One is a free running test in the waves. The other one is a captive test in the waves to capture the hydrodynamic force characteristics acting on the ship motor. Here's just, some ship published the paper about the free running test in the waves. So free running in not only in regular waves, but also in the irregular waves. So then nowadays many papers were published. Here, so I would like to introduce a special technique for measurement of the ship position. That is a total station system. Total station system is a fully wireless system for position measurement by applying some optical technique. So you can see that this is a photograph about the camera of the total station. Camera part is here. So then this is as a part of the head of the human. So then this one has one eye. This is the eye. So using this camera, so then this camera always watching the target. This target is the prism. So then the prism is installed of the ship model. This camera of the total station can track this target position automatically from the tank side. So then this, you can see this drawing is not, ship model, actual boat. This drawing is showing that the situation of the measuring the some, water depth in the river. Total station systems come from originally civil engineering field. By applying this total station system, Kim measured position of the maneuvering in waves. So then the ship model is here. The prism is installed at this point 4 and the midship point. So then for measurement, Kim used 2 total stations. So wave is coming, head wave and also beam wave. So then Kim measure the motion of the maneuvering waves. This is a result. This shows the turning trajectories in regular waves. So then you can see many, lines. So then first one is that this is a turning with rudder angle 35 degrees. Wave height is a 2% ship length. So wave direction is here. Ship moving from here to this direction. So then is this position, 0, 0 position, that's the origin. It just starts the steering. So then at the same time is such kind of turning start. This is a trajectory in car mode. So then reach the steady state turning situation. Wave is coming here. So then there's a trajectory in the waves. Some deformation occurs. You can see the ship is moving here. This is a trajectory in regular waves with lambda by L equal 1.0 here. Lambda is a wave length, L is a ship length. So then the wave direction is here, but drifting during the turning, such a direction is here. So the directions are different. So you can see some broken line, colored, orange colored this one. This is also the trajectory in case of lambda by equal 0.7. And also green line. This one's the results in lambda by 0.5. Generally, the ship drifts in a direction different from the wave direction during turning. The direction of the drift differs depending on the wave length to ship length ratio. Okay, lambda by 1.0 is here, but 0.7 is here. So then this lambda by 0.5 is here. So this drifting direction more close to wave direction in a shorter wave length. And also the ship significantly drifts in shorter wave lengths. So this is a drifting distance here in the shorter wave cases. This distance is quite large to compare with in the case of lambda by L1. So such kind of, this is a really typical characteristics of the ship turning in waves. Using the total station, not only maneuvering motion, but also wave-induced motion, such as the heave motion during turning. So then you can see that this blue colors and this one, this is a heaving during turning, experimental data. But condition is slightly different. Lambda by 0.7, so wave direction 9 degrees. Beam wave cases. In beam wave, the trajectory shifts like that. Blue color means experiment, red color is a calculation. Drift direction is quite different. Drifting direction is quite different from the wave direction. So then is of course during the turning, where wave into the motion, the total station system can capture well. And also just to compare with the experiments, so the calculation result shown here. So then and also this is a comparison of the drift angle. And also this one is a yaw rate. Experiments, calculation, experiments, calculation. This calculation captures well the tendency of the experiments. This calculation was made by applying the 2-time scale method. So then the next I would like to introduce the outline of the 2-time scale method. 2-time scale method is a really convenient, and the computational time is short, accuracy is not so bad. This method is was presented by Skejik and Palutinsen in 2008, and also at the same time, Yasukawa and Nakayama also presented. In this method, total ship motion, that means the maneuvering waves. Maneuvering waves is expressed as some low frequency maneuvering motion and high frequency wave-induced motion. So then this is two models, low frequency motion and high frequency motion are separated solved. About the model of the low frequency maneuvering, we use the car motor maneuvering model with the mean wave forces. About the model of the seakeeping, so normally we can use the time domain strip method or time domain 3D panel method. So then there's two models separately solved, but the information exchange is really important between two low frequency and high frequency model. From the low frequency maneuvering model, we can get the ship position, ship orientation, the ship speed. So then such information is shift to the high frequency keeping model. So then we can calculate the high wave induced motion. So then based on such data, we can calculate the drift forces. This information is moved to the maneuvering low frequency motion. Such kind of iterations sometimes used. This is an outline of the 2-time scale method. Okay, next move to talk about the experimental the method. So this time I would like to introduce the wave-induced motion and the mean wave forces of a ship obliquely moving in regular waves. If this is a very important point, is a ship is moving obliquely. If the ship is moving straight, that's the usual seakeeping problem. So then there's this experiment was conducted by Yasukawa Adnan in 2006. So then I'd like to introduce some results about the wave-induced motion, shape and pitch, sway and roll. In that case, it's only in head wave. In head wave, so then the heave and the pitch in a 0 degree, the completely same as the usual seeking problem. Then the horizontal axis is lambda by L, so that results in regular wave cases. Taking the sum drift angle 5 degree and 10 degree, but this drift angle effect is not so remarkable in heave and pitch. But in the sway and roll, in 0 drift angle cases, sway and roll amplitude should be 0. In the experiments, almost 0. But drift angle, taking the drift angle 5 degree to 10 degree, so then the sway and roll, such lateral motion appears. This indicates some coupling between the longitudinal motion and the horizontal motion is existing in ship obliquely moving cases. So at the same time, we measure the added resistance, steady lateral force, and steady yaw moment. Added resistance, this characteristic is almost the same as a normal usual straight moving cases. But taking the sum, drift angle 5 degree to 10 degree, steady lateral force is induced with a steady yaw moment. Such kind the really interesting characteristics appeared when the ship moving obliquely in waves. But unfortunately, such kind of experimental results, the number of the paper were huge. Okay, so this time, so I introduced two-time scale method. But this method is based on linear theory. Linear theory means the wave height is small. But nowadays, CFD become really powerful tool for simulating the everything. So then the maneuvering the waves cases, CFD is really important, especially direct simulation using the CFD is really promising. So then the 2012 carried out some simulation. So then now is extending to the problems, cost keeping control, and the turning circle and the zigzag maneuver. Okay, this is the result about Wang et al. 2018. So then this one is a simulation of the turning in regular waves. So then there's of course, clearly we can capture the free surface elevation during turnings here. At the same time, we can check the vertical structure around the sepal during the turning. So I think that this method is really promising in near future. Okay, next move to minimum power requirement problem. Background. IM adopted energy efficiency design index for new ship to reduce the shipping greenhouse gases emission via improved ship design and operation. There was a concern that one of the most effective ways of reducing the EDDI is simply by choosing a smaller main engine, thus consequently reducing the ship's design speed. Within IMO, a debate took place on how far speed reduction could be used to attain a low level of EDI. As a result, it was decided to limit the use of this method of EDI reduction so that it does not lead to unsafe and underpowered ships that may lose maneuvering capability under adverse weather conditions. Under that background, we gave the task that here. So then this I will introduce some results. So then unfortunately not time, so just mention about the problem. Revision on 2013 internal guideline. So for determining minimum propellant power, there are the two methods. One is a level 1. So using some really simple formula. So then the other one is we call level 2. So sometimes called as a simplified assessment. This level 2 method is now really important. This name, this is the assessment name is putting the word simplified, but not so simple because first we have to define the condition. Adverse weather condition, we have to define that condition and also define the advanced speed. So after defining some condition, we have to calculate the resistance, commutator resistance, aerodynamic resistance, added resistance waves, and appended resistance. After fix the resistance, based on such data, we can calculate the engine power. So then the required advanced coefficient. If we want advanced coefficient, we need self-propulsion factors, thrust deduction, weight fraction. So then using such data, we can calculate some power. But there are several problems. First one, adverse weather condition. A rational adverse condition, it is very difficult to fix one. So that the second one is added resistance waves. And also, it is very difficult to predict added resistance waves correctly. And the third one is the propeller load difference in a car motor and in the waves. So then there's a self-propulsion factor. How should we determine? So there is such a kind of a problem, but at present, no conclusion have been reached. So then there's that conclusion. So then there's but unfortunately, the time is limited to just to show the slide about prediction method of ship maneuvering waves. We should move to some experiments and calculation in irregular wave with large wave height. And the direct shift simulation is promising, but direct shift manual simulation in regular ways are still a challenging problem. Minimum engine power requirement now is discussion is continuing in the IMO. The recommendation to improve the numerical method, we need some more better understanding of the mean wave drift forces. Then in the cooperation with the CKIP committee is really important. We should provide a captive test data for validation with the CFD, such as oblique towing test in the waves, circular motion test in the waves, PMM waves, and so on. Investigate the effect wave height and propeller's performance on the coupling with the main engine cooperation with the propulsion committee. Thank you.
Thank you, Professor Yasukawa. Thank you for the presentation with the summary of the state of the art and the activities of your committee. I understand that maneuvering in waves is a complex problem, and the specialist committee on maneuvering in waves are difficult terms of reference, actually. Not so easy to solve. But the importance of this problem is increasing for future ships, especially with regard to IMO, and also related to safe and auto navigation. So there's one question come up before from Hussein Gaemi regarding the power level reduction. Could you please comment on the MEPC's submission that suggests the speed under adverse weather conditions at 2 knots?
Mm-hmm.
And now there is a submission of Korea which suggests 4 knots as a minimum ship speed. And the discussion of this matter is currently going on in MEPC, but according to my experience as a neighbor, it could be 0 even in adverse conditions. But for calculation, you have to define something. So what do you say to that?
Okay, thank you for discussion. So then there's in MEPC 7651, the revised draft guidelines were discussed under the reinforced adverse weather criteria, wave height 6 meters, wind velocity 22.6 meters per second with a ship speed 2 knots were proposed. However, UK and the Republic of Korea prefer the conservative approaches, the ship speed 4 knots on this issue. In MEPC 7654, Korea concluded that when the revised draft guidelines are used, the lower required minimum power could be derived as shown in the figure 1. Okay, this figure shows the change of the required propulsion power. Yeah. So this graph, bar graph, the results of the using in a 2 knot cases. So this is the order magnitude is slightly different, but this one is a self-propulsion factor is different. This result is the 4 knot. In the case of 4 knot, minimum power are increasing. So then the increasing means there exists some margin in the engine is bigger. In the case of 2 knot, the minimum power should be smaller one. So then I think in view of the safe ship navigation, larger minimum power is better. So in that case, in that opinion, 4 knot may be better. But in view of the reduction of the CO2, smaller engine is better. In that case, we should choose the 2 knot. So then this line, suitable line, it is very difficult determine this line. So then now the ship speed under the advanced weather condition 2 or 4 knot is not fixed yet. It is scheduled to be discussed at the ongoing MEPC meeting. Thank you.
Okay, thank you. Any other questions? No, then.
I received a question from Professor Yong-Fan Kim.
Okay, I think that's the one I'm going to ask you. That's a conventional maneuvering model such as Abkowitz or MMG models for core calm water assumption. Yeah, most of the existing models are based on such models and extended to waves by adding second order mean drift force and moments, as you showed in your presentation, due to waves. He would like to ask you how much you think that such approach is accurate. That's one question. And do you think it's possible to develop a more thorough mathematical model, including wave and sea-keeping components in the maneuvering model?
Okay, thank you. Yeah. Low frequency maneuvering waves can be predicted with practical accuracy by a simple treatment, adding the second order drift forces acting on the ship to the maneuvering simulation force model in calm order. This may seem surprising, but the rationality of such handling has been theoretically proven on the assumption that the wave height is low, ship speed is slow, and the ship is slender. On the other hand, it is difficult to grasp the ship maneuvering large waves, which is important for discussing the navigation safety by the theoretical prediction. For the prediction in such a situation, it may be promising to use a method based on CFD. That is our answer about the first question.
It won't be so easy with the CFD to include all this. Okay, the next question of Professor Kim was, you pointed out very precisely that the turning trajectories in waves are dependent on wave conditions such as wavelengths, amplitude, and that was even in regular waves. Now, in case of irregular waves, he's sure that the trajectory is dependent on the wave generation parameters, including the number of wave components, phase difference seeds or wave components, and so on. For example, the trajectories can be different for different wave seeds. Then we need to have a consensus on the general definition to define directors in irregular waves. Do you have any comment to that?
Okay, so the answer is the only way to rationally capture the motion characteristics of a ship in irregular waves is to repeat free running tests changing the seed. We think the CKIM committee is discussing how to handle the ship motion in irregular waves. On the other hand, for turning in irregular waves, the effect of the slowly varying second order wave forces seem to be small. In such a case, it is useful to normally repeat the turning test in regular waves with different seeds. Based on the test results, we can obtain the turning indices such as advance and tactical diameter in irregular waves, and can take the average and the standard deviation based on those. In such a way, it is possible to capture the turning characteristics in irregular waves. Thank you.
And there was one more question. According to his experience in adverse seas ocean environment, the sea-keeping component due to heavy waves can play a role in ship maneuverability. This is, the ship can have large motion, varying displacement and velocity in harsh environment, and these can provide significant influence on the ship maneuvering. If so, just adding the second order mean forces due to sea keeping in the maneuvering equations is not enough. And you have to include instantaneous sea keeping components in the ship maneuvering simulation. And my personal experience is that you even can have the propeller getting out of the water. So, and how do you calculate that? Because
Okay, thank you.
have any comment to that?
Yeah, calculation method based on the concept of the two-time scale method cannot accurately predict ship motion in large waves because usual two-time scale method based on a small wave. So we think the CFD based direct method are promising. Yeah, that is my answer.
So no way.
Experiment is better.
Okay, experiment is better. Thank you very much. I think we have to close this session and in time, so it's okay. There was no further question coming up. Thank you for your presentation.
Thank you.